Hello everyone. In this video I want to start a sequence of video where I'm going to cover multivariable calculus. And this video I'm going to start explaining what is like parametric equations. So first, let's remind ourselves what have we studied in single variable calculus. In single variable calculus we have studied functions in terms of one variables. So the goal of multivariable calculus is to revisit the function of one variables and generalize the tools that we have studied in single variable calculus, such that the tools are differentiation and integration. And we want to do differentiation integration for the function in terms of more than one variable, so f, x of y. But there's another way how we can generalize our way of seeing single variable function. It's to use parametric equations. Okay, so let's take this function y equals f of x. And we can see in this function that x is independent variable and y is going to be dependent variable. So one of the way how we can revisit our single variable function is just make x to be dependent. And how I'm going to make x to be dependent? I think the best way of seeing this, let's consider an example. Let's take one of the most simplest functions, y equals x squared. And for this function, we want to make x to be dependent variable. So one of the way how to make x to be dependent variable is just make x to be a function of some variable, of another variable. Because we can see that y is dependent of x, it means that y is in relation of x corresponding to the function f. So in this case, let's make just x equals to t. Then if x equals to t, I can see from y equals x squared that y is going to be equals x squared, so y is equals to t squared. So by having the function on the left hand side, I can write this function in such way that x is going to be dependent and y is going to be dependent variable. And such representation are called parametric equations. Okay, so the first thing, before I'm going to continue, the function on the left I like to call Cartesian equation. And the function on the right hand side I will call parametric equations. So the first thing that we want to ask ourselves, why do we need these parametric equations? And the reasons why, if we're going to write function in terms of as a parametric equation, we're going to have more information. What does it mean, like more information? Let's plot y equals x squared. And we know that the graph of y equals y squared is going to be just parabola that goes from these 2 points. So we're going to have this parabola y equals x squared. And what about parametric equations? You can guess that for parametric equations I'm going to have the same function. Why? Because basically we have the same object, parabola, and parametric equations is just another way of writing down the equation for our function. But what is the difference between parametric equations and Cartesian equations? The difference how we're going to plot this function. So for Cartesian equations, we first choosing that x equals to some variable 0, let's say, and then y equals to 0. So we're plotting first finding the x value and then finding the y value. But what about parametric equations? For parametric equations, we have parameter t. So when t equals to 0, from here I'm getting the 2 points at the same time, x and y. So x equals to 0 and y equals to 0. So I'm getting this point. So when my parameter t will increase, for example, like t equals 1, I will get another point, x equals to 1 and y equals to 1. So on my graph I will get this corresponding point, 1, 1. So what the x transformation do I have here? I have the direction on my graph. So in other points we can think about this equation as equation that describes the path of some particle. Let's start at the origin, and t is going to be our time. So when t increases, we're gonna see on our graph in which direction my particle is going to move. The next thing I want to discuss, what if we're gonna have another parameterization of our function. So let's say we're giving some time interval t where it changes from 0 to 2. And then I can easily see for parameterization x equals t and y equals t squared, I want to find the corresponding path that my particle is going to travel for t when it changes from 0 to 2. So when t equals 0, I will have point x equals 0, y equals 0. When t is equals to 1, I will have point x equals 1, y equals 1. And when t equals to 2, I will have point x equals 2 and y equals to 4. And let's plot these points in the graph. So this is going to be my point for t equals 0. This is going to be my point for t equals 1. And this is going to be point for t equals 2. So we have this graph. And let me give you a little bit notation. So this point is called initial point, because graph starts at this point. And this point called terminal point, because it's a point where my particle stops. Okay, so we can see when t changes from 0 to 2, this is my path. But let's choose another parameterization. For another parameterization, I'm going to choose, let's say, x equals t squared, because when I choose my function x to be my variable x to be a function of some variable t, I have a freedom of choice, and I decide to choose, okay, let's do like t squared. And we have the same time period. So what I'm going to get in this case? So let's first draw my Cartesian coordinates, and let's plot the same 3 points. So let's say we have t equals 0, t equals 1, and t equals 2. And here, for the first point, I will get the same point, x equals 0, y equals 0. For second one, I will get x equals 1, y equals 1. But what about the third one? For the third one, I will get that x equals to 4 and y equals to 2 to the fourth, 16. So the path that my particle traveled is going to be bigger. So we can see when I change my parameterization, so let's say this is 16, no, it's not 16, that's my 16, let's draw like this. This is 4, this is 1, okay, you got my point. So the path that we travel is going to be longer. So when we choose a parameterization, we're going to change how far my point is going to travel on my original path, which was parabola in this case. So when t changes from minus infinity to infinity, I will have the whole path, but if I will restrict to some finite interval, I will get a finite path. And different parameterization will have the different length of for my part. There's a different length that my particle has traveled. And in the future videos, I'm going to discuss the different parameterization will give the concept of velocity. We're going to see this when we're going to take derivatives of parametric functions. Parametric functions, I mean like parametric equations. So functions written in terms of parameter t are called parametric function. Thank you for watching this video. I hope you enjoyed. If you have any questions, just let me know. And in my next video, I'm going to discuss a couple of examples of parametric functions and their graphs. If you're not subscribed to my channel, please subscribe, and bye-bye.